Hey guys, this is Ed with the Kaizen effect. In today's video, what we're going to do is continue our discussion on Lagrangian mechanics, and in particular, we're going to continue talking about calculus of variations because, as I've said in previous videos, physics is like the philosophy of life translated into the language of mathematics. So if you want to understand physics, how to use it, what it entails, what it's trying to describe, you must understand the underlying language, the underlying mathematics that drives it forward. In terms of Lagrangian mechanics, the language we're going to speak in terms of is calculus of variations. So you got to understand this language, you got to be comfortable with it, and for that reason, what I'm going to do is I'm going to continue working on examples. I'm going to work on one more example to try to build up your intuition with the tools we developed in my previous video where I derived the Euler-Lagrange equation, and I want you to be comfortable with this language such that you can speak it freely, understand it's trying to communicate, and then use that understanding of that language to jump into Lagrangian mechanics and become a master at what you're studying, okay? Now, the example we're going to run through today, it's a little different from the previous examples we've ran through. Previously, we ran through a lot of geometric examples, which we were trying to derive certain things using the Euler-Lagrange equation. This example I'm going to run through today is a bit physics-based. Aside from Lagrangian mechanics, you can use these tools to prove some physical ideas and principles. So what we're going to do is that. We're going to do just that in this example. The example we're going to run through is a classical one. It's known as the Brachistochrone problem. And this is the problem of trying to find the shortest amount of time that is needed to get from one point, which I'm going to put at the origin of this graph here, to another point 2 at some arbitrary location on your graph in the vicinity of everything you're analyzing, okay? And you want to find the path that's going to allow this particle to travel due to the force of gravity alone, so we're going to have no friction or anything like that, to this second point in the shortest amount of time, okay? Now, this problem is called the Brachistochrone problem. I think that's appropriately entitled because if we take a look at the word, you can see right here, Brachistochrone, a little strange. If we break this up into two different root words, brachistos actually refers to shortest. It's a root word for shortest, and chronos refers to time. So when we combine the two, this is like the shortest time, the problem of shortest time, okay? Now, in order to solve this problem, we're going to use the language and framework we've put together of calculus of variations. In particular, we're going to use, again, the Euler-Lagrange equation. So the point of this example is to help build your intuition, get comfortable with using this. So I think it's a good idea to, once again, review what's going on here. Okay, so the Euler-Lagrange equation is given as follows. It's the partial of f with respect to y is equal to the derivative with respect to x of the partial of f with respect to y prime. Okay, now the important thing to realize here is that when we use calculus of variations that I showed in my derivation, if you have not watched that, check it out right here. You got to understand that before you proceed here because that's the underpinnings of everything we're going to study here. If you come across something you don't understand in this video, I highly encourage you, check out that video, study what I'm doing, because in order to fully understand these tools and this framework and take advantage of it, you need to understand how it was derived and what we were varying in the problems we looked at in that derivation to understand what's going on here. But just a quick recap. So what we did was we varied these different paths to guarantee a minimum or a stationary point. And we did that by taking this y variable. We said that defines the path that we're varying, and the path is going to be defined by this independent variable. In this case, it's x, okay? So it's important to realize that because you could take this equation, change the variables, but it has to follow that same pattern. And in this problem, we're going to do that. We're going to change some variables up, and I'm going to do that such that you gain an understanding of the underlying ideas with this function, or rather this equation, the Euler-Lagrange equation. So again, the y variable defines the path that we're going to vary. The x variable here is the independent variable that arises out of the integration by parts we use in the derivation. If you don't remember what I'm talking about, go refresh your memory, check out that video. It's a really great video. I go into a lot of detail in the derivation, so don't miss it before proceeding with this video, okay? So the Euler-Lagrange equation is meant to take this function here, and it's trying to minimize some kind of functional, okay? Again, a functional is a function of a function. We see that applies here because this is a function of function, and then, we have all the paths inside here. So in order to use this, we're going to try to find stationary points of a function we want to minimize. In this case, it's s, and we take the f under the integral, which is a function of the path, the derivative of the path, and the independent variable x. So we take this guy, and then we throw it into this guy, and that allows us to minimize the functional that we're talking about, okay? So obviously we're going to use this, and I want you to feel comfortable with this. You got to understand this stuff, but in order to use it, we actually need a functional to minimize, okay? So what I'm going to do here is I'm going to look at the problem we've defined here, and I'm going to try to put together a functional that's going to allow us to minimize the time, because again, we want to find the shortest time between these two paths. These 2 points. We want to find the path that results in the shortest time of travel between these 2 points. That's a more concise way of saying it. So let's actually try and figure out how we do that. So we want to find a function for the time, okay? What we're going to do is we're going to say the time delta t, which is going to be t2 minus t1, so the difference between when we start and when we end, is going to be equal to the integral of ds, which is some path. We're going to say, okay, maybe the function looks something like this, okay? ds is going to be the length over here. But what we're going to do is we're going to look at one small portion. Again, let's blow this baby up. So we're going to say there's some path here. We're going to call it ds. And then we're going to have, dy. If we use the axis here, which I will explain in a bit, why I have this sort of weird axis system here. We're going to have differentials dy and dx. So we're looking at a very infinitesimal element, and then we're going to add up all those infinitesimal elements along this curve. Again, that should raise a red flag for calculus, especially for the integral, okay? So that's why I'm using the integral here. So we're going to add up all these guys, and if we divide by the velocity at each point along here, what is that going to give us? That's going to give us the time, right? It's going to give us the time. So if we take a look at the units here, this might help make this a bit clearer. If this is meters, we're using the SI system. We have meters for the distance along here. We're going to measure that in meters. And our velocity is going to be in meters per second. We see the meters are going to cancel. And then the seconds are going to jump up on the top. That gives us a time, okay? So this is what we're going to do. We're going to take every infinitesimal particle, or rather length along this path here, and we're going to calculate this ds over v. We're going to calculate the second to traverse that infinitesimal piece, and then we're going to add up all those pieces in total. That's going to give us the total time to go from point 1 to point 2, okay? So I'm going to put a 1 and a 2 here. However, we need a way to figure out how to calculate that ds, and we're also going to have to figure out a way to calculate the v. As I'm going to show shortly, that's going to come from our physics. That's why I say this is more of a physics-based problem as opposed to just a geometric problem. So, it's a bit more interesting than the previous ones we studied. So let's figure out what ds is. Now, I've done this multiple times in previous videos. I'm going to run through it again because it's a little different. Don't let this confuse you. We're just going to change up variables, because what we're going to do is we're going to be defining x in terms of y. I'll show you why shortly. But let's just derive that here, okay? So we can take this infinitesimal part here. We can use the Pythagorean theorem again, and we know that the hypotenuse squared, ds squared, is equal to dx squared plus dy squared, right? So let's work with this a bit more. If we take dy out, if we want x to be the path that we're going to define everything, and we want y to be the independent variable, I'll explain why in a bit. Don't let that freak you out. We pull out the independent variable again, the dy squared, and then this becomes dx over dy squared plus 1. Again, we did not change anything here. If we multiply dy squared through, this guy cancels out. We get a dx squared plus dy squared. Same expression. We didn't change anything here. So what I'm actually going to do, I'm going to also take the square root. And this allows us to pop out that dy. So we get x prime sub y, this is the derivative, squared plus 1 square root dy, okay? So that's how we're going to define the differential ds, and we're doing this such that we can add up all these increment dy's, the increments of our independent variable as such. So we're going to use this for ds. Now, we have to figure out how to calculate the v at each infinitesimal points along this curve. I'm just going to erase this to get some more board space. How do we do that? Well, we need to actually go back to our physics, okay? So how can we relate position to velocity? Well, if we look at the problem here, we're starting at the origin, and the particle is going to be released, whatever object it is. Maybe we're going to say it's a particle here. It could be any object. The object or the particle is going to be released at the origin at x1 equals 0, y1 equals 0. So I'm going to further define this. It's going to be 0, 0. And then it's going to travel down to x2, y2 on a path such that we minimize this guy right here. So what we see is that if gravity is acting down, we have a ton of potential energy here. So when we let it go, the gravity wants to pull it down. We're going to take that potential energy. It's going to be converted into kinetic energy. And that's how we're going to get this velocity here. So we see that from energy principles, we can relate the potential energy, which is a function of the distance between these two, to the velocity. Okay, so let's do that. So we're going to take all of our potential energy and we're going to find, let me erase this a bit. I'm going to put the G down here. We're going to define this distance as y. And this is why we're setting up the origin as such, because we're trying to get to this point. And after that point, we don't care what happens. But we want to take all the energy here and convert it into kinetic energy. So the distance between this point and this point is going to be the potential energy that's converted into the kinetic energy, right? So this is going to be the distance y between these points. So the energy we're starting out with is mgy. So we're thinking we had it down here, we pulled it all the way up here. And just to flesh this out a bit more, to make you feel comfortable with all the definitions you've been looking at, we know that the work is the negative F dot dr. Okay, so the gravity is down, and we're pulling this guy up like that. I'm going to call r. We're pulling it all the way up a distance y, so we'll call this y. And I'm going to put a j hat there because it's in the direction, the y direction. So if we're pulling this guy up y, you know, cosine 180, or rather, we have r like that, we have g like that. This angle is 180 degrees. So this is going to be negative mg vector dot r. Okay? Now, this can further simplify down to negative mg r, which is just y. We take the scalar variable here. Cosine 180, right? Because g dot r is going to be the magnitudes, the absolute values, times cosine of the angle between them. We see the angle is 180. This is a negative, so this gives us mgy. So y is the distance that we pulled it up. We're going to say this is the bottom. We're setting this as our bottom. We pulled it up a distance y, and that gives us this guy. So that's how I'm getting this guy here. That's why it's positive, and that's how you can make use of all these standard equations you have that you're given in Physics 101. So we're going to take that. We know all of it is going to be converted into kinetic energy, and we're setting up our system here such that this is the bottom, so it's not going to have any more potential energy, okay? So we see here that we can isolate y, or rather v, in terms of y. That's why y is being our independent variable here, because we want everything to work out here. So we're going to take, I guess I'll do it backwards. It doesn't matter. So we cancel the m's. We bring this to 2gy. We take a square root. Bam. That is our v. And we want this to match up with our axis. So this is why I'm defining y as going down, because the further this point goes down, it just changes the height. So the height is tied to our axis, and that just makes it a bit simpler to work through the mathematics here. So this is what we're going to use for our v, and we've already defined ds. So we can take those quantities and plop them into this equation. So when we get that, or rather when we do that, we end up with the integral of x prime sub y squared plus 1, that had a dy out there, divided by root 2gy. Okay, so we're going to integrate from y1 to y2, and we can further simplify this a bit more. We can take out this 1 over 2g, so this is a constant, and then y1, y2, then we have x prime sub y squared plus 1 over y, take the square root, bam, this is the guy we're going to use as our function now. We're going to minimize this guy, and then we're going to proceed from there. However, I realized that I actually didn't talk about something I wanted to talk about, which is why this was actually such a classic problem. And back in the day, they didn't have calculus of variations. So what we're doing here, by getting this function now, plugging it into the Euler-Lagrange equation right here, and then minimizing this delta t, this nice framework wasn't developed yet, but interestingly enough, it actually came out of this problem, which makes it such a classic, important problem in physics. But what happened was, one day there was a challenge. They came up with this problem. How could you find the path that results in the shortest time between these 2 points? Some mathematicians. Actually, the Bernoulli brothers proposed it. And what they did, they sent it out to mathematicians, and it was a big challenge. They had to come up with a solution, send it in, and then it was published in however they published stuff. Maybe they had journals back then, I'm not sure. But what happened is there was a duel between Newton and all the other people, because Newton is famous for coming up with the framework of calculus, making that formal, because again, he used the language of calculus to speak his physics, solve his physics problems, and he was attributed to inventing it. And a lot of people would say, no, you didn't invent this, it was around beforehand. So there's some arguments between Newton and Bernoulli when they were actually solving this problem, which was pretty interesting. But Newton actually solved this in a day using some really clever tricks. He didn't use calculus of variations. He used, I believe, a lot of geometric stuff to solve this. And he solved it very quickly one evening, came home, didn't sleep until he got it solved, and then sent it in, got it published. So Bernoulli solved this, Newton solved this, Leibniz solved this, and also L'Hopital, the guy with the weird name that looks like El Hospital. So these guys all solved it, and what happened was maybe like 50 years later or something, Euler came around. He started looking at these problems and he was like, wow, I could take all this framework and put it into a nice kind of mathematics that could be used to solve problems of this nature all the time. So he started doing that, and then Lagrange came around and said, oh, this is pretty cool stuff. Let me formalize that a bit more, and that's where calculus of variations came from. So this is a very classic problem, very important problem. This is like the pinnacle of calculus of variations. So it's exciting to take the framework we have now and solve this and show how easy it is to solve it now, when back then it was a monumental challenge. Each mathematician came up with different solutions and different ways of solving this, which is pretty amazing if you think about it. Back in those days, they came up with some really ingenious stuff. But coming back to the problem, what we're going to do is, we got this function now. We defined the time between point 1 to point 2 on any kind of path. And what we're going to do is, we're going to take this function out. We're going to find stationary points by restricting all the paths connecting these 2 points to the one path, the subset of all paths that satisfy the Euler-Lagrange equation. And when we do that, it's going to minimize this and get us the result that we want, which is the path that leads to the shortest time between these 2 points. All right, so now we have the basic setup, all the framework for the problem of using the Euler-Lagrange equation to minimize our function now, which is the time, and find the path that leads to the shortest time between these 2 points. Let's actually run through the problem, figure out what that is, and solve it. Okay, what we need to do first in order to solve it is reformulate the Euler-Lagrange equation to actually correspond to the function now we got here. Now, we know if we look at the Euler-Lagrange equation here is that we need to figure out what f is. F is the function under the integral for the function now, and in this problem we can see that this guy is f. Yet we have to question what's going on here in comparison to this one. And I want you to pay a lot of attention to this one, because this is going to be different. So if you feel comfortable with this after running through it, I say you're really good with calculus of variations. If not, maybe you should check out the derivation video I put together and study it a bit more. Make sure you understand what these variables are, because this is intended for you to build your intuition such that you feel comfortable with everything, and also to let you see the power of these tools and what they're actually capable of outside of Lagrangian mechanics. So what I want you to realize is that, again, the y variable here is the variable of the path we're varying, okay? And the x variable here is the independent variable, okay? In our derivation, we said that y is going to be our independent variable. And we did that to make it a bit easier because we have a y down here. We want everything to be y on this, in this function, because if we had x's here and y's here, then what would we integrate? Okay, this just makes the problem nicer and easier. Okay, so what you need to realize is that this function now is different than this one. Our path is defined by the independent variable y, and our path is in terms of x. So this is actually a function of x sub y, x prime sub y, and y. Okay? So when we go to use this guy, we're going to have to reformulate it. What do you think it's going to be? Can you see what it is? Let's take a look. So using this, we know that this variable has to be the variable for the path. We're saying the path is x. So this becomes df dx equal to the derivative with respect to the independent variable. Here we're saying y is the independent variable. So this becomes d dy df d x prime. Because again, we want to use the derivative of the variable that's defining the path. Here, that's x, because it's x sub y. Okay? So this is the Euler-Lagrange equation we're going to use. And we're going to use this guy as our function now, the function f, that we're going to plug into this. So obviously, we need to take the derivatives, the partial derivatives. Let's start with that. Let's start doing that. Okay, so the first thing we're going to do, we're going to take df dx. So df dx. Luckily, we see here, there's no x here, so this guy becomes 0. And we also have df dx prime. Okay? And so in order to do that, we got an x prime here. So we're going to differentiate this. We end up with, we're going to take first, we're going to pull out 1 over root y, and then we're going to differentiate the square root of x prime squared plus 1. Okay? So we're going to have to use the chain rule here. So first we have x prime squared plus 1. That's the 1/2 here. So we multiply by 1/2, and we subtract 1 in the exponent. It's the product rule, right? So we end up with that. Then the chain rule, derivative of the thing inside. So the derivative of this is 2x prime. So the 2's cancel, and we got to divide by the root y. What we end up with is x prime over square root y x prime squared plus 1. Okay? So that's the df dx prime we have here. And the important thing to realize is that whenever we have this guy here, df dx equal to 0, we can see that this term here is going to be a constant, right? Because the derivative is 0. It's not changing. So anything inside here has to be a constant. So that means when we plug this guy into here, that guy is going to be constant. So let's write that down and then erase that to make some more board space. So we know that x prime over the square root of y x prime squared plus 1 is going to be a constant c. Okay? So the next thing we need to do, since we're defining the path in terms of x, we got to isolate the x primes and then solve for x. And what I'm going to do first is I'm going to do something strange. And this is facilitated by my understanding of the problem. It might make you feel a little uncomfortable, but you'll see where I'm going shortly. So I'm going to define this constant as another constant. Let me take a look at my notes and verify I'm using the right thing. Okay, so I was correct. So we're going to define this as 1 over 2a. All I'm saying is that this constant c is going to be a new constant. This a is another constant, so it's still a constant, right? If you divide by a constant, you still have a constant, right? So I didn't change anything here. So we're going to isolate x prime. And we're going to do that by first, I'm going to first square this. So let me back up a bit. I sort of messed this up. So first I'm going to square this, okay? When we square this, I'm going to go like this. I'm going to just put an arrow here. We're going to end up with x prime squared over y times x prime squared plus 1 is equal to the constant squared. So constant squared is still a constant, and now I'm going to define the constant squared as 1 over 2a. All right, so now we want to isolate x prime. So we end up with x prime squared is equal to, or rather I'm going to multiply this 2a over here, and that's going to be equal to y times x prime squared plus 1. So what we want to do is take the x prime squared over there, so we get x prime squared times 2a minus y is equal to y. So the final thing we end up with here, which we're going to have to integrate to get the final result, is that x prime squared is equal to y over 2a minus y. So we could take this squared term, take the square root, and bam. This is going to define the path that leads to the minimization or stationary point of delta t. That's going to be the minimum in this case for delta t. That's going to find us the shortest time connecting these 2 points. It's going to give us the path that we want, the answer to the Brachistochrone problem. Okay, so we're making some really nice progress. Let's keep chugging along and try to wrap up this baby. So we have an expression for the path again in terms of x prime, okay, in terms of the derivative. So what we want to do is, this is dy dx. No, it's dx dy. Tripping up my own self. So what we want to do is we want to take that dy over there and we want to integrate. We want to add up all these incremental parts. Okay, so when we do that, we get the following. We get x is equal to the integral of dy. And you see this integral, this nasty integral, and you're thinking, what in the world am I supposed to do? Well, what you have to do to solve this is you have to be very clever. You have to use some wise thinking and some trial and error. What we're going to do is we're going to use a substitution. It's a trigonometric substitution. And when you see this, it's going to bother me. If I saw this, it would bother me too, because I like to see things spelled out. I like derivations, but this is an instance in which you can't really derive this substitution until you actually give it and work through it, because this is something based upon intuition, experience, and what you know works with integrals. So the thing that's really driving this, that you'll see as I work through it, is trigonometric identities. Whenever you have something with a something minus y variable on the bottom, usually that's a code word or an indicator that you can use trigonometric substitution. In particular, you want to use something like 1 minus cosine squared, 1 minus sine squared, such that you can take advantage of trigonometric identity. So I'm going to give you the substitution we're going to use. I'm going to work through it. I'm going to try my best to explain why we chose that as we work through it, and hopefully make you comfortable with that. Because I know if I was saying this, it would really piss me off if somebody just gave me the substitution, didn't explain it. But there's nothing more to explain here until we actually work through it. So what we're going to say is we're going to let, or I guess I'll, in terms of board space, I'll do it over here. We'll let y equal a times 1 minus cosine theta, okay? And it's going to become apparent as I work through it again, so relax. So what we need to do is we need to figure out how to replace the dy too. So we need to take the derivative, dy d theta is equal to a sine theta. And that is because when we differentiate cosine, that gives us a negative sign. So the negative drops away. So next what we want to do, we want to solve for dy. So we can multiply by the d theta. And we end up with that. So that's how we're going to convert this over. That's how we're going to take advantage of this substitution. So I'm going to put that in red here. That's important. And then we're going to bring that guy up there. So when we do this, we're going to end up with the following. So we get x is equal to the integral. We'll plug in y here. So we get a times 1 minus cosine theta divided by 2a minus a 1 minus cosine theta, and all this is under the square roots. So now we need to replace the dy. So I'm going to need a bit more room. I'm going to erase that. So outside of the square root, we just plug this guy in. We get a sine theta d theta. Let me make this a bit bigger. it's easier for you guys to see. So again, we get A sine theta d theta, okay? So you're probably looking at this and you're thinking, well, gee, that substitution you gave me doesn't make any sense. Why would you choose that? Well, to understand why, we're going to have to work with this a bit. So what we're going to do is we're going to pull this guy out, put it in front of the integral sign. So we get A integral, and then we're going to take the sine term and bring it into the square root. And this is where I was talking about trigonometric identities. So in order to bring this in, it becomes sine squared, right? So we end up with, again, the square root of sine squared theta, because sine squared, the square root of sine squared equals sine. So we didn't change anything here, times A times 1 minus cosine theta. This is all going to be over. Now, this is why I put the A in here, okay? This is why I put the A here, such that we can pull this out. So I'm going to pull out the A, and then we end up with 2 minus 1, so that becomes 1, minus minus, so that becomes plus, cosine theta. All right? And then we also have the d theta still. So I know what you're thinking. You're thinking, okay, now we're in an even worse situation. What are you doing here? What are you doing? So the key thing here is to realize that this sine squared term, this guy here, we want to use a trigonometric identity. So we know that sine squared theta plus cosine squared theta is equal to 1. So this guy is going to become 1 minus cosine squared, okay? So I'm going to erase that and plug this guy in. And that is going to give us the result we want. So when I plug that guy in, we get this 1 minus cosine squared theta. Okay, now we need to simplify further. So we need to factor this, and that's when everything is going to start to click for you. So this has to be equal to A times the integral of, this is 1 minus cosine times 1 plus cosine. You see where I'm going here? So first of all, we can cancel this A, and then this is going to be 1 minus cosine theta times 1 plus cosine theta times this guy, the 1 minus cosine theta, divided by the 1 plus cosine theta. All right. So this term here, this guy, that is equal to 1 minus cosine squared. If we multiply this through, we get a 1 plus cosine minus cosine. The cosines cancel, minus cosine squared. That's where that's coming from. So this is where it comes into play. We got this 1 plus, we get the 1 plus. That cancels, and then this becomes squared. So we have 1 minus cosine squared. If we take the square root, this ends up being just A times 1 minus cosine. Okay, d theta. So it's pretty easy to solve, right? So when we integrate this, this is where the substitution comes into play. We run through all this, brings us to a nice expression we can integrate, and what happens is we end up with A times theta minus sine theta plus a constant, right? We need that constant in there. So this is the path for the x term that we end up with. All right, so we had to go through all that work, all that trouble, just to find a parametric expression for this curve in terms of y and x. So our parametric variable here is theta, and when we change theta, that's going to give us the coordinates for the x and y of this curve. So we found technically the curve that is going to find the shortest time between these 2 points if gravity is the only force acting on the particle or object traversing this path. However, there's still more that we have to work through. Before I go through that, now you can see why I used this substitution here, because that helped us actually get to that point in the integral that allowed us to solve it, and that's why it was used. It came through trial and error, through trying a lot of different things, experience, and the important thing to realize is whenever you get that, that square root, some quantity minus some quantity cosine or sine, that triggers the red flag. You raise your red flag. Oh my God, this is an opportunity to use trigonometric substitution. That's why I use that, and I use this particular form to actually make it work. Okay, so we end up with this term for x, and there's one thing left. We must find the constant c. How do we do that? Especially with that parametric equation here. Well, what we need to do is, first we need to find the theta for which we get the known values of x and y. Because we know at x1 and y1, it's passing through the origin. So we know that at y equals 0, 0 equals a 1 minus cosine theta. So what would theta have to be to guarantee this? Well, that's easy. When theta is 0, cosine 0 is 1. That would cancel this out, so theta must equal 0. Okay, so at theta equals 0, x also has to equal 0. So theta equals 0, x equals 0. Then we can solve for this guy. So we plug in 0 for x, has to equal a, and plug in 0 for theta, so it becomes 0 minus sine 0. Get rid of that shit. Plus a constant. Well, sine 0 is 0, right? 0. So this whole thing is 0 here. And then we can solve for c. So after that, we find that c is 0. Bam, we solved what we're looking for. So this guy just drops out. And now we have the exact solution to our problem. The question is, well, what does this portray? Like, what does this look like on a graph? So let's take a look at that. Let's take a look at that now. Actually, before we do that, there's one more caveat. We would have to define a, but I'm not going to do this here. However, a is going to be a characterizing parameter of the curve we see, but we could solve for a by using this information here. So the x2 and y2. We must solve for a such that x and y are equal to x2 and y2 at the same theta. Okay, so that's what we would have to do. I'm not going to do that here because, again, as you're going to see, a is going to define the curve and give it some definition. So let's actually plot out what this guy looks like. So we're starting here. This is x1, y1. We're going to point 2. I'm going to put it down here. x2, y2. What does this curve look like? Well, this curve is actually what is known as a cycloid. So it's going to look something like this. And then it's going to keep going and repeating, so on and so forth. Now this is basically like the bottom rim of a tire or wheel with a radius. Let's say, I don't know, the center might be up here, but this is going to have a radius of A, okay, for this parameter. So that's how the A term is going to change this curve. And furthermore, it's important to realize that this is why I chose this A. This is why I chose this A back when we had that constant, when we had x prime equal to blah, 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 equal to a constant, right? I chose 1 over 2a such that we could make this work and also get this parameter that I knew was going to define the cycloid, okay? So another really important thing to realize about this is that, this is going to solve the Brachistochrone problem, but it also solves something else. Let's say this is point 1. Let's say this is point 2. And let's call this point 3. Now, the time it takes to go from point 1 to point 3 is actually going to be the same time it takes to go from point 2 to point 3. So this is also the solution for another problem, which is called the isochrone problem, or isochronous problem. I'm not sure how they actually pronounce it, but the idea here is iso is equal, chronos is time, so that's the problem which you have the same time when you go back and forth in some kind of curve. So, if you start here, you go up to there, well, that would never happen if you don't have any exterior force, but you see what I'm saying. You come back down, you're going to have the same time. So it also solves the isochronous problem, which is pretty interesting. The really interesting fact about that is you can use that to actually put together clocks. You can take advantage of this by, maybe have some kind of thing. I'm not sure how it works exactly, but you could have something going back and forth, and the fact that this time is the same regardless of where you start on the path allows you to keep track of time. There are a lot of famous clocks that actually use this mechanism. There are some in a museum in London. Got the name written down here. I actually forget what it is. It's the Victoria and Albert Museum. Again, that's in London. Very famous clock. But it's sort of weird that if you start here, you get to point 3 in the same time. So why is that? It's because of the conservation of energy again. So, let's take a deeper look at that. So if you have mgy equal 1/2 mv squared, we see that v is, you're going to start with no velocity here, and then it's going to pick up, and then it's going to get it's hard to explain. The thing I'm trying to say is that, when you're here, you're going to take a while to pick up that velocity. But if you stay on this curve, it's going to pick up in such a way that the time is the same along these paths, which is really interesting. It's a really, really interesting problem, but that's, it's due to, this relation here. I mean, work with the velocity here. Try to figure out what it is and how much time you would have to traverse, because, if we start here, the y is going to be smaller, so the v is going to be smaller at the end, so it's going to take a bit more time to get there, even though you have a smaller path to traverse. Similarly, if you start up here, you're going to have a long path to traverse, but the velocity down here is going to be much larger, so that compensates for the difference, right? And it just so happens that the time, if you release a particle from here for it to get to there, is the same as if you released a particle from here for it to get to here. Which is really, really interesting. But this wraps up our second, or I guess it's our third example for calculus of variations. I sort of tricked you in a way by messing around with how the Euler-Lagrange equation is defined here, and that was done on purpose because you got to understand this language. You got to understand calculus of variations. If you do not understand this, how can you use it to do practical things? How can you unleash the power that's behind it? And how can you do Lagrangian mechanics? So if you were not comfortable with this, go back to my previous examples, look at the derivation, understand the underpinnings behind the derivation, because you might have to look at it a few times. They say that you have to look at something about 7 times to permanently know and understand what you're looking at. So go back as many times as you have to, but again, I was trying to build an intuition with the calculus of variations here for you, and I wanted to demonstrate the power here, how it can be used outside of Lagrangian mechanics. The big takeaways from this example and this lesson again are that when you have the Euler-Lagrange equation, what it's doing is it's saying that if we have some kind of function L s as defined as such, we can take all the possible paths that can connect these 2 points, and we're going to restrict the path that we want to pay attention to the path or the subset of paths that satisfy this equation here, and that is going to minimize the s here. The important thing to realize is that our function now is going to have a function f, which is defined in terms of y sub x, y prime sub x, and x. Here, x is the independent variable that's used to define the path defined by y, and in the Euler-Lagrange equation, df dy, the y variable here is always in terms of the variable defining the path. That is the same for the y prime here, and the x variable is the independent variable that's used to actually define the path y. Okay, so you got to understand that, because we're going to use a ton of different variables in Lagrangian mechanics. We're going to look at things known as generalized coordinates, so make sure you understand that. If you guys don't understand this, hit me up. Send me an email at ed@the-Kaizen effect. Leave a comment below. I'll try to answer it. I want to help you guys out. I want you guys to understand this because, again, physics is the philosophy of life translated into the language of mathematics. If you don't know the language, you can't speak the physics. You can't understand what it's implying, and you're not going to go anywhere with this stuff. You're not going to take advantage of it. So please send me an email. I can sit down with you one-to-one. I offer a ton of services. I also offer life coaching services to help you out with anything else you're having trouble with. I want to help you guys as much as possible. So again, send me an email at ed@thekaizeneffect.com. Check out my stuff, my free content at www.thekaizeneffect.com, and I'll help you reach your goals. I'll do whatever it takes to help you out. And I hope you enjoyed that. Keep charging ahead. Keep working towards your dreams, and I'll see you in the next video. The example problem we're going to work on is a classic problem in calculus of variations. This is the problem known as geodesics. How to find geodesics in geometry. What does that mean? Basically, a geodesic is like the smallest or the shortest path on any kind of geometry. Now, in the previous video, I showed you how to prove that the shortest path between 2 points on a plane is a straight line, and that makes sense, and that's intuitive. And furthermore, that helps us show that when we apply this, we can get a result that jives well with our intuition, right? Because we would expect the shortest path between 2 points to be a straight line. Now, what happens if we want to do that with something that's not as intuitive? If we want to take any kind of geometry and find the shortest path between 2 points, how do we do that? How do we solve that kind of problem? Well, we're going to do that right now in this video by applying Euler-Lagrange equation with function L to find the shortest path for any surface that we encounter in nature. Alright, so how exactly do we do that? I'm going to show that by applying the same ideas to a cylinder. We're going to do that for the geometry of a cylinder, and I'm going to generalize that such that you can do it for any kind of geometry you encounter in